the particle will undergo a transition from n equals to 3 to n equals to 2, then that will emit a radiation of frequency nu, and the energy of the radiation equals to energy of the third energy level minus energy of the second energy level, that is E3 minus E2, equals to h nu. On the basis of this proposition, Planck formulated the following expression, that is called Planck's radiation law, and for explaining the experimental observation of the black body radiation. So this is the Planck radiation law, that is rho lambda t equals to 8 pi hc divided by lambda to the power 5 e to the power hc by lambda kbt minus 1. So here kb is nothing but the Boltzmann's constant, and the value of the Boltzmann constant equals to, that is kb equals to 1.3806 into 10 to the power minus 23 joule Kelvin inverse. That you have to remember. And c is nothing but the velocity of light, that is equals to 3 into 10 to the power 8 meter per second. And here T is the temperature in Kelvin scale. So according to this Planck's radiation law, that could explain the black body effect. But according to the classical mechanics, it was unable to explain the black body radiation. But the Planck's radiation law successfully explained the black body radiation by the particle. Now coming to what is quantization? Let us try to understand the meaning of quantization. Let us imagine a ball at the top of an incline. It would have a certain potential energy that is equal to MGH, depending upon the height on which the ball is situated. Now, as the ball rolls down the incline, it could take up any of the possible potential energy values. On the other hand, if we have a small ball at the top of a step podium having some height as that of the incline and allow the ball to fall stepwise, then the podium will take the podium, it could have only a few possible potential energies determined by the height of the step from the ground. That means if the size of the ball will be very small, then the ball will move to downward stepwise. But if you will take a bigger ball, that will continuously. So that's why this quantum mechanics is applicable for the microscopic particles. While the behavior of the ball, so rolling down incline, if the ball will be a bigger ball, then that will behave classical behavior. But for small ball, that will obey the quantum behavior. Now coming to the quantization and photoelectric effect. So we can visualize the light which falls on the metal. So now we'll discuss a little bit about the photoelectric effect. To explain the experimental observation of the photoelectric effect, he proposed that the light is made up of small packets of energy, that is called quanta, and in case of light energy, that quanta is also called photon. Now each packet of energy carried by the wave has energy equals to h nu, depending upon the frequency of the radiation. This was in contrast to the classical view of light in which the energy is spread over the whole wave. Thus, we can visualize the light which falls on the metal as a stream of photons. That is that small packets of energy. If the energy in the form of light energy, that is called photon. But any form of small packets of energy, that is called quanta. So the incident photon transfer their energy to the electrons of the metal. Now, if the energy is sufficient, then the electrons on the surface of the metal, the electrons overcome the attractive pull to the neighboring species and immediately ejected out. This phenomenon is called photoelectric effect. That here immediately, and sufficient. So these are two important if the incident on the meta surface is sufficient. Immediately the electron which is bound on the meta surface that will remove minimum amount of energy we take an electron from the surface of the metal, and that means that minimum amount of energy required to remove an electron from the surface of the metal, that is called threshold energy. That means the energy which will fall on the metal surface, that definitely should be greater than equals to the threshold energy h nu naught. And further, we can see that if the incident photon had a frequency greater than the threshold frequency, or in other words, the energy greater than that required to eject an electron, then part of the energy of the incident photon is used to knock off the electrons, whereas the rest of the energy become the kinetic energy of the ejected electron, and hence immediately the ejected electron will move in a faster velocity. So this is an excellent agreement with the experimental observation. Still further, we increase the intensity of the light. If we increase the intensity of the light, maintaining the constant frequency, then more number of photons will strike on the metal surface, and hence more number of electrons will be ejected from the surface. Since all the photons of a given frequency have the same energy, the kinetic energy of the ejected electrons does not increase with intensity. Thus, all experimental observation on the photoelectric effect could be fully explained in terms of concept of quantization of radiation that proposed by Einstein. Now coming to quantization and line spectrum. So for this, you should recall the postulates of Bohr's model that you have studied from your 11th class. The electrons moves in a circular orbit around the central stationary nucleus, like the planets move around the sun, and Maxwell's classical theory of electromagnetism do not apply the atomic scale. So these things you have already studied. The electrons are restricted to move only in a certain particular orbit in which the energy of the electron is quantized. It can be take only certain discrete values, in contrary to the classical belief where the energy is continuous, that could have any value. So according to classical mechanics, the energy could have any value, but according to quantum mechanics, the energy of the electron is quantized. That means the energy of the electron will be some certain discrete values, not arbitrarily any values. So, so these orbits are called stationary orbits, or non-radiating orbits, or shells, etc. As long as the electrons moves in a particular orbit, the energy of the electron remain constant. When an electron changes its orbit from one initial energy state EY to the lower EI to a lower final energy state EF. Suppose the when an electron changes its orbits from initial higher energy state EI to a lower final state energy state EF, a single photon will be released, and the energy of the released photon, that will become h nu, which is equals to the energy difference between the initial and final energy state. In other words, the frequency nu of the emitted radiation is determined by the separate of the energy levels of the two stationary states. Further, the electron could be excited from a low energy initial state to a high energy final state by observing a photon having, of energy which is equals to EF minus EI. And the third and next the fourth postulate, the angular momentum of an electron of mass me moving in a circular orbit r, that is mvr. So if m is the mass of the electron, then the angular momentum is quantized, that is mvr equals to nh by 2 pi, where n is the positive integer, that is called principal quantum number. Now, again, you should remember that from this Bohr's theory or from this Bohr's model, we can get the following expression for the radius and energy of the nth atomic orbit. So here, this is the radius of the nth atomic orbit, that is Rn. So Rn equals to A naught into n square, where A naught is called Bohr's radius, that signifies the radius for the orbit where n equals to 1, and that is called the ground state. And similarly, you may remember the energy of the nth orbit En equals to minus Rh into 1 by n square, where Rh is nothing but the Rydberg's constant, and having the constant value this one, that is me z square e to the power 4 divided by 8 h square epsilon 0 square. So this is one constant that is called Rydberg's constant. Now, according to the postulate 3, what we have discussed above, the energy emitted in the transition of a single electron from initial energy state of energy Ei to the final energy state of energy Ef, that is epsilon, the energy difference h nu equals to Ei minus Ef. So h nu equals to minus Rh whole into 1 by Ni square minus 1 by Nf square, which is equals to Rh whole into 1 by Nf square minus 1 by Ni square. Here the Nf and Ni refer to the quantum number of the final and initial energy state respectively. And again we know that nu equals to C nu bar, where nu bar is the wave number, because we know that nu equals to hc by lambda. So here nu equals to C nu bar, where nu bar is the wave number. Now in place of nu, we can put hc C nu bar. So that is having the value this one. And hence nu bar equals to minus Rh by Hc whole into 1 by Nf square minus 1 by Ni square. So this equation is identical in the form of one obtained experimentally from the line spectrum of the hydrogen atom. Thus, the Bohr's model provides an explanation for the observance of line spectrum for hydrogen atom. Now coming to consequences of quantum mechanical nature of the microscopic world. So the two systems, so there are two important phenomena with no equivalence of the microscopic domain. So the two important phenomena are wave particle duality and uncertainty principle, that we'll discuss here. That we have also studied from intermediate level. So the wave particle duality, that is a phenomenon unique to the quantum mechanical world, that is the microscopic domain. Quantum mechanics means that it deals with microscopic domains, that means that deals with the mechanics of very small particles like atoms, molecules, electrons, nucleus, etc. To understand the wave particle duality, we should first remember the particle and wave behavior. Suppose I throw a pebble stone into a water. What you will observe? The pebble will slow down, and therefore it will just go down to the curved part of the bottom of the water. On the other hand, if we allow some light to pass through the water taken in a beaker, it will get refracted. That is, it will slow down and bend towards when it goes more rarer medium in air to the denser medium of the water. So what we will find that this behavior, it is quite different from that we had in the case of particles. Now let's take another case and see what happens when you pass a wave and a particle through a slit. You know that we know that a light wave gets diffracted when passed through a slit. You may observe a similar behavior with the water waves when they meet some kind of obstructions. We find so these are the explanation of the wave particle duality. So we will directly go to the wave particle duality. So the wave particle duality, the de Broglie generalized the dual nature of light. De Broglie generalized the dual nature of light and all type of particle and proposed that the ordinary matter like electrons and protons etc. can have wave-like properties, and the wavelength associated with such particles is related to the momentum, that is p, and hence lambda equals to h by mv or lambda equals to h by p. So here p is the momentum of the particle and h is the Planck's constant and v is the velocity of the particle. If this were to be true, it is then these so-called particles would show the phenomenon of diffraction and interference that are characteristics of the wave behavior. So according to this equation, one example is there. You can see that is example number 1. Calculate the wavelength associated with an electron having a velocity 100 km per second. And you can directly apply this equation. We know that lambda equals to h by mv. Now in place of h, just wait 1 minute. Okay, so in place of h, you can put the Planck's constant, and m is nothing but the mass of electron, that is 9.019 into 10 to the power minus 31 kg, and v it is already given, that is 100 kilometer per second. That means 1 into 10 to the power 5 meter per second, and finally we will find that the wave associated with the electrons, the wavelength associated with electrons, that is 7.27 nanometer. So this wavelength is of the dimension of the internuclear distance between the atoms in a crystal. And another question is there: calculate the de Broglie wavelength for a spherical droplet of radius 0.1 millimeter of water moving at a speed of 1 meter per second. So here mass of the droplet, so first you have to calculate the mass of the droplet, that is the density into volume of the droplet, because here the so radius of the droplet is given, and from the so radius you can calculate, as that is spherical in nature, you can calculate the volume v equals to 4 by 3 pi r square. So putting this value you can find out the volume, and again we know that the density of water, that is 10 to the power minus 3 kg per meter cube. So hence mass of the droplet equals to density of the droplet into volume of the droplet. So you have calculated the density and volume, then find the mass of the droplet, and after that you will apply the de Broglie's equation, and you can find that lambda equals to h by mv. So putting h as the Planck's constant, here mass of the droplet, and here velocity is given 1 meter per second, then you will find the wavelength associated with the spherical droplet. Now, as per the fourth postulate of the Bohr, because in the Bohr's theory, the fourth postulates of the Bohr's theory, it is given that angular momentum of an electron moving in a circular orbit is quantized, that we have discussed just now. Now let us see. So here we will match or here we will describe the Bohr's postulates. That means we will see that whether the Bohr's postulate is valid, is validated by the de Broglie's equation or not. Now the fourth postulates of the Bohr theory, that is given that angular momentum of an electron moving in a circular orbit is quantized. Now let us see the de Broglie's idea. So according to the quantum mechanics, electron moving freely in a space and traveling like waves. However, these are bound, that is are under the influence of the nucleus, so they behave like standing waves. So that means so that will not behave like a free wave because the electrons are negatively charged and the nucleus is positively charged. So when the electron is circulating around the nucleus, so that is the electrons are under the influence of the nucleus. So the wave nature of the electron will behave like standing waves. So these waves occupy some region of the space which is possible only if the circumference of the orbit, because electron in the electron that is circulating around the nucleus in that orbit, if the circumference of that orbit is 2 pi r for a particular state, and within that 2 pi r integral number of waves should be there. Integral number of waves means n number of complete waves should be there. Complete wave means the wave, if the wave contains one crest and one trough, that is called one complete wave. So that means this one is called one complete wave. This is the complete wave. And the length of the complete wave, that is also called wavelength, because because we have studied that wavelength is nothing but the distance between two consecutive crest and two consecutive trough, and also it is the distance of a complete wave. So that is called lambda. So if the circumference of the orbit in which the electron is circulating around the nucleus, that is 2 pi r, for a particular orbit for a particular energy level n, and if the circumference of the orbit is an integral multiple of the de Broglie wavelength, then 2 pi rn equals to n lambda. That means 2 pi r of the nth orbit should be equals to n number of, that means whole number of lambda. So here 2 pi rn equals to n lambda. And again from the de Broglie equation we know that lambda equals to h by mv, or lambda equals to h by p. Now substituting this value in this equation 2 pi r equals to n lambda. So we can write in place of lambda, if we'll put h by mv, we can write 2 pi r equals to nh by mv. Now rearranging this, we can write mvr equals to nh by 2 pi. So that what we have studied in the Bohr's model. So which is the Bohr's postulate on quantization of angular momentum. So having justified the Bohr's postulate on the angular momentum, we can say that each quantum state or each orbit of the Bohr's model with the quantum number n can seen as stationary wave of the electron equals to n number of wavelength. That means whole number of wavelength. So here you can see one example is there. So here in this orbit, three number of wavelengths are there, three complete waves are there, and again for this orbit, four complete waves are there, and here five complete waves are there. Now coming to another principle, that is called Heisenberg's uncertainty principle. Uncertainty means, that means something error will be there, not accurate. So these important consequences of the wave particle duality of the nature was discovered by Heisenberg, and that is called uncertainty principle. So according to this principle, Heisenberg pointed out that the wave nature of the matter leads to a significant and far-reaching conclusion has no method of measurement. However, carefully if it is performed, that can reveal both the exact location and momentum of a particle. So that means, according to the Heisenberg's uncertainty principle, just wait for 1 minute. Okay, so according to Heisenberg's uncertainty principle, it is impossible to measure simultaneously the exact momentum and exact position of a microscopic particle like electron, nucleus, atom, molecule, etc. That means simultaneously you cannot measure the exact position and exact momentum of the microscopic particle. So if we measure the exact position, then there will be some error in its momentum, and if we measure the exact momentum, then some error in the exact position. So simultaneously you cannot measure both the exact position and momentum of a microscopic particle like electron, atom, molecule, etc. And here, if we measure the exact position x, so here mathematically the symbol of the position is given as x, and similarly the symbol of the momentum that is given as px. So if we measure the exact position x, then there will be some error in the momentum, and that error is known as del px. So here del is given for the error. And in the other hand, if we measure the exact momentum of the microscopic particle, that means if you have measured the exact momentum, that is exact px value, then there will be some error in its position, that is called a del x. And mathematically, the Heisenberg's principle can be expressed in terms of an inequality, that is del x into del p greater than equals to h cross by 2. So here h cross is h by 2 pi, and hence, so here graphically, so here that means the del x is uncertainty in the position, and similarly del p is uncertainty in the momentum. And the Heisenberg, according to the Heisenberg's principle, that is mathematically expressed in terms of the inequality, that is del x into del px or del x into del p is greater than equals to h by 4 pi, that is h cross by 2, because we know that h cross equals to h by 2 pi, h by 2 pi, that is called h cross. H cross is h by 2 pi, and hence putting the value of h cross, we can write del x into del px is greater than equals to h by 4 pi. And if the particle is at rest, its exact position is known, and the uncertainty in the position del x will be equals to 0, and the uncertainty will be in the momentum del px will be infinite. And similarly, that is m del v equals to infinite, and the particle will have the kinetic energy and cannot be at rest. That means the particle cannot be at rest according to this equation. So here, so the first unit deals with the introduction of quantum mechanics, how the quantum mechanics arise. So all these things you have studied from your previous classes. Now we will move to the actual, that is introduction to wave mechanics. So the first one is postulates of quantum mechanics. Now coming to the postulate number 1. So this is the postulate number 1. So this first postulate proposes a function analogous to the classical displacement of to describe the quantum particle. Now, according to the central postulate, so the postulate will start from here. The behavior of a single particle is described as a fully the behavior of a single particle is described as fully as possible in terms of an appropriate wave function, that is psi. So psi is a function of x, y, z and t. So x, y, z means that is the position coordinates, x-axis, y-axis and z-axis, and t is the time coordinate. That depends upon the coordinates of the space, that is x, y, z and time t. For a system consisting of two particles, So the postulate, so the up to this, that is the postulate. This is the postulate number one. Now coming to the explanation, for the system consisting of two particles, the wave function would be, so if there will be two particles, the wave function would be psi x1 y1 z1 x2 y2 z2, but the time that is t, that is both same for the two particles. And for a general system of I particles, it can be written as psi qit, where qi represents the spatial coordinates of all the particles of the system. Now, for stationary state, in which all the observables of the system are independent of time, the function can be represented as the product of space-dependent amplitude function, because for the stationary state, so if the wave function of the particle psi xyzt, so it can be considered as time dependent function. Now it can be considered as the product of two functions. The first function is the position function and the second one is the time function. So that is psi equals to, so this one is psi equals to some small psi xyz into f of t. So this coordinate amplitude function, so this is the small psi xyz, that is called amplitude function, contains all the information of the system in the conservative force field, and this can be retrieved by using a suitable quantum mechanical operator that we'll discuss in the later section. Now, this point onwards will work only about the system of conservative force field, where the energy is constant and the wave function is so represented by Schrodinger amplitude function, this one. So here we will consider only the wave function as xyz. So according to this postulate one, the wave function must have some attributes to be an acceptable wave function. So according to the postulate one, the wave function associated with the particle should be an acceptable wave function. Acceptable wave function. So these are so acceptable wave function means the wave function must be single valued, continuous, and finite. So if the wave function will satisfy these three conditions, then that is called acceptable wave function. So for acceptable wave function, that should be single value, that should be continuous, and that should be finite for all the values of the coordinates, and must be smoothly varying within the boundary where it is going to be zero. So that means at the boundary, the wave function will become zero. In other words, we can say that the wave function must have these attributes throughout the configuration of space. So a wave function with these attributes, that is called well-behaved wave function. That means if we select a particular configuration of space, and within that configuration of space, if the wave function will be single valued, continuous, and finite, that is called well-behaved wave function. So here you can see that is the schematic representation of some wave functions that are not well behaved. That is the first figure A. So this is not well behaved because the wave function has three values of x. So here, if you calculate the position coordinate, the value of the wave function on x-axis, and here we have taken one particular position x1. So at x1 the wave function having three values, so one value will be here, and this is another value, this is another value, and hence this wave function is not single valued, that is having three values. So this is not well behaved wave function. And coming to the next one, in the figure B, the psi x is not continuous. So here the wave function is a discontinuous manner, and that's why this is not well behaved. And figure number C, the wave function is not smoothly varying at x1. So here it is not, so some deviation is there. So that's why this is also not well behaved. And psi x is not finite between x1 and x2. So you can see, so between x1 and x2, the wave function having infinite value. So that is not finite. So for a well-behaved wave function, these three, the wave function should behave these three conditions. The first one is that should be single valued. The second one is that should be continuous, and the third one that should be finite, and also that should be smoothly varying. So here ascertain whether the following wave functions are well behaved or not and give the reason. So this is the wave function f of x equals to e to the power plus 2 e to the power plus 2x plus minus 2x. So here the curve of this wave function e to the power 2x, and this is e to the power minus 2x. So you can see the solution, the wave function has two different values and most values of the x, and it is not a single valued wave function, so that's why this is not well behaved. Now coming to second one, the second one is f of x equals to x square plus 2. So this graph is like this, and as the value of the x goes to the infinite, the function also become infinite, therefore it is not acceptable wave function. So if the value of the x will be infinite, then the wave function will become infinite. Now f of x equals to e to the power minus x square. The wave function is finite, continuous, and single valued at all the values of x. So if you take any value of x, the wave function will give rise to single valued, and this is having finite values, and the finite value is so it goes from 0 as x approaches either infinite or minus infinite. If the value of the x will become infinite or minus infinite, the f of x will become 0. Therefore it is a well behaved and acceptable wave function. You can see this is one acceptable well behaved wave function. Okay, so now we will see that from your intermediate level you have taken two waves of the same frequency and amplitude moving in opposite direction. There will be superposition of these waves, and the resultant amplitude of the wave is given as psi xt equals to 2a sin kx cos omega t, which is equal to psi x cos omega t, where omega is the angular velocity. You may note that the value of the amplitude is a product of two functions. One is dependent upon the position and other is dependent upon the time. So the position the position of the nodes remains same at all times, and the wave function is called standing and stationary waves. In general, the standing waves arise in the region in which the waves can propagate that have different boundaries. Short standing waves are central to wave mechanics, and these are represented by stationary waves. So that means having the wave having some boundary, that is called standing wave. That is the state of the system where the measurable property of the system do not change with time. And again you should remember such idea was proposed by Bose also. It can also shown that the time independent wave function of a classical stationary wave, that is given by del square psi equals to minus 4 pi square by lambda square psi. So here del square, so that is called one operator, so that we will discuss in later sections. So del square, so that is one operator, that is equals to del square by del x square plus del square by del y square plus del square by del z square. So here so again we will discuss these things after the discussion of the operator. Now coming to the postulate number 2. So the postulate number, according to the second postulate, so in the first postulate we have considered this was the wave function. So in the second postulate, the wave function psi xyz for a single particle in a stationary state can be obtained by solving the second order differential equation, that is called time independent Schrodinger wave equation. So sometimes derivated as TISC, that is time independent. So that means here we have not taken the time coordinate. So here that's why that is called time independent Schrodinger equation. And the time independent Schrodinger equation, so this one is the time independent Schrodinger equation that is in equation 2.9. So this one is the time independent Schrodinger wave equation, that is a square by for a particle moving in x-axis. So minus h square by 2m d square by dx square plus vx lambda psi equals to E psi. So within the square bracket, that this term represents the total energy of the system and the total energy operator, that is called Hamiltonian operator. So the Hamiltonian operator, that is called the total energy operator. So the Hamiltonian operator or total energy operator can be mentioned by another operator, that is called H cap. So this is the time independent Schrodinger direction only. So Hamiltonian operator as H cap, equation 2.9 can be written as H cap equals E. Now operator. So operator is nothing but the introduction or Hamiltonian. Hello, hello. Now is it audible now? Hello. Okay, okay.
Yes, sir.
So here operators are mathematical instructions. For example, d by dx instruct to take the derivative with respect to x. Whatever may the functions follows it. And the function on which the operator operates, that is called the operand. Now here in general, an operator when operates over a function to change the function to another function, a cap operates equal to g, that will give rise to a new function function g of x. In this, identify in terms of a cap or a cap or some x or a function. And similarly, if the operator is d by dx and the function is 4x square, then d by dx of 4x square that will give rise to 8x, that is a new function. And similarly, if the operator is d square by dx square, the function will be sin x, then d square by dx square sin x equals to, so that means that d by dx of sin x, so that will give rise to that will be d by times, and hence that will find minus I. So that so when so this is when an operator and a constant, then the operator is called eigenvalue operator and the function is called eigenfunction and the constant is called eigenvalue. The called eigen operator and the function is called eigenfunction and the value and the constant is called eigenvalue and the equation is called eigenequation. Now coming to postulate number 3. So in the postulate number 3, according to this postulate, the quantum mechanics, there is quantum mechanical operator a cap associated with every observable, measurable means observable dynamic property such as energy, momentum or position, and if the dynamic property of the system can be determined exactly by the experiment, then the possible exact value of the dynamic property can be obtained by the following eigenvalue equation. Again, I am so repeating the postulate: momentum or position. This is the third postulate. In other words, the quantum mechanical operator for a given dynamic property, when operates over an amplitude function of a particle, it provides the value of the property. For example, the information about the linear momentum in the ground state of the particle restricted to move in x dimension can be obtained by operating the linear momentum operator, this one. So that is called linear momentum operator minus I h by 2 pi d by dx over the ground state of the function particle moving one dimension. So here the wave function will be psi equals to square root of 2 by L sin pi by Lx. So here the ideal is position and the corresponding operator is that is the operation is multiplied by y, and position along the z axis, that is z cap, the operation is multiplied by z, and the linear momentum along x, the x component of the linear momentum, that is called px cap, and here the operator is h cross by I d by dx or minus I h cross d by dx. Similarly, the linear momentum along y component along z component are similarly same values. And coming to the kinetic energy operator, that can be written as t cap, and the operation is minus h cross square by 2m del square. And potential energy operator, that can be written as v cap, the operation is v of xyz, that is multiplied by v. Now coming in general, a given operator for a specific system may have infinite number of eigenfunctions. Each one of these will give the distinct equals a. Now it is like this. Check whether the operator for linear momentum in the x direction, that is minus ih cross d by dx, is an eigen operator of the function e to the power I nx or not. So here we know that a cap psi equals to a psi. Here in place of a cap we will put this one according to the question. In place of psi we will put e to the power minus inx. So here that will give right minus I h cross d by dx of e to the power minus enx. So that is d by dx of e to the power inx. That will give rise to in e to the power inx, and here another constant I h cross is there. So I h cross into in into e to the power inx. So that will give rise to minus I into I, that will that is minus I square, that is 1. So that will give rise to nh cross e to the power inx, that is nh cross e to the power inx. Hence this function, hence the operation e to the power minus inx, and having nh cross. And another 5 minutes of break, and after that again we will start. So one theorem is there. You can see if two eigenfunctions psi1 and psi2 of a linear operator A cap have same eigenvalue A, then any linear combination of the wave function will also be an eigenfunction of the same operator A cap with same eigenvalue. Then that you have to prove. So here, according to this theorem, it is given that two eigenfunctions psi1 and psi2 and one operator is A cap for the two eigenfunction and psi1 and psi2 having the same eigenvalue A. That means A cap psi1 equals to small a psi1 and A cap psi2 equals to small a psi2. Now let us take the linear combination of the wave functions are, if suppose psi equals to c1 psi1 plus c2 psi2, c1 and c2 are two coefficients, then A cap psi equals to A cap of c1 psi1 plus c2 psi2. So as A cap is a linear operator, so A cap psi equals to A cap c1 psi1 plus A cap c2 psi2. So that is A cap psi equals to c1 A cap psi1 plus c2 A cap psi2. So in place of A cap psi1, we will put small a psi1. So that will give rise to A c1 psi1. Now in case of A cap psi2, we should put small a psi2. That will give rise to A c2 psi2. So which is equals to A whole into c1 psi1 plus c2 psi2, which is equals to A psi. Thus we find that the linear combination also eigenfunctions of the same eigenvalues. Though we have stated and proved the theorem for the two functions, it is true for any other number of such functions. Now the question is, evaluate x to the power n cap commutator of x to the power n cap px cap. So here you will take any function f of x and you will find out the value of the commutator. And the second is, under what condition is the following is true, that is a cap plus b cap whole square equals to a cap square plus ab plus b cap square. Now coming to Hermitian operator. So Hermitian operator, so this is the definition of Hermitian operator. An operator A cap is said to be Hermitian if and only if it will obey the following condition. What condition? Integration of phi 1 star A cap phi 2 d tau equals to integration of phi 2 A cap phi 1 star d tau, where phi 1 and phi 2 are two well behaved complex value wave functions. This may be same or different. Let us check whether the linear momentum operator. So this is the definition of Hermitian operator. This is the definition of Hermitian operator. This is the up to the, so you have to write up to this. So this is the definition of Hermitian operator. Now whether this may be same or different, so we'll check that. Now the question is, we have to check whether the linear momentum operator in the x dimension is Hermitian or not. Let us consider the two operators phi 1x and phi 2x are two well behaved complex valued wave functions of variable x. So let us consider two well behaved complex valued wave functions phi 1x and phi 2x. So A cap is the linear value. A cap is the operator that is called linear operator, and integration of phi 1 star x A cap phi 2 star x dx equals to integration of phi 2 x A cap phi 1 star x dx. We know that the linear momentum operator along the x-axis. So that means in place of A cap we have to put the linear momentum operator. And if we put the linear momentum operator in case of A cap, the function will be like this, and rearranging that we will find that. So rearranging this, we can find that simply simplifying and so rearranging, we can find that this will equal to 0. So now we need to show that the term on the left hand side equation indeed that equal to 0. We know that for the two general variables u and v, the integral product equals to integration of u dv plus v du. For our wave functions, this one derivative of the LHS of the wave function, this one, that is d integration of d phi 1 x phi 2 x. So here integrating we can write phi 1 x phi 2 x. The value of x ranges from a to b. Since we have taken the wave function to be well behaved wave function, they must vanish the boundary, and we can write an operator over a acceptable complex wave function psi n yielding the eigenvalue an. So here a cap psi n equals to eigenvalue an psi n. Now we can write the complex conjugate of this expression, that is a cap star psi n star equals to an star psi n star. Now multiplying this equation 51 by psi n and integrating, we can we have to multiply psi n here. We have to multiply psi n star, and here also we have to multiply for this equation 51. We can write integration of psi n star a cap psi n d tau equals to integration psi star, and here a cap psi n d tau, a cap psi n will equal to the eigenvalue. Okay, so we can say that an so an is it can be true if an will be a real number. Therefore, we can say that the Hermitian operator give real eigenvalues. Thus, we conclude that all quantum mechanical operators must be linear and Hermitian so as to ensure the real observables of their average values. Okay, so for the rest part, we will discuss on the next class, that is on Monday. So the Monday we will discuss the remaining part of the quantum mechanics.